So hello, my name is Eugenio Perez. I work for Red Hat as a senior software engineer, and I've been working in the Shadow Virtqueue solution for a couple of years.
Hi everyone, my name is Gautam Davar. I'm working as a senior manager software development for AMD, previously Xilinx. I have a huge team of 2 people, including me, who developed the vDPA-net driver. So we are close to upstreaming it, so should be there in a while. But if you find any bugs, you can totally hold me responsible for them. So yeah, we'll go ahead then. So this talk is about vDPA-net live migration with Shadow Virtqueue. I'll cover the basic concepts first, and then we define the problem that we see with SRIOV VF pass-through when we are trying live migration, and how vDPA comes as a solution to that problem. We then demonstrate live migration demo across 2 different hosts which have hardware NICs from different vendors, and then we dive deep into Shadow Virtqueue operation. I understand most of you already know about SRIOV, but single root IO virtualization is actually a concept that allows a single PCI device to be shared across multiple VMs as they see them as different physical devices. As you can notice here, you require a vendor-specific driver within the guest OS for it to be operational. So as the specification calls out, there is a physical function which represents the physical device, and there are multiple virtual functions noted here as VFs, which are passed directly into the virtual machine, and the data path bypasses the host kernel. So VM migration typically is very common, and what we understand from it is that we can migrate a virtual machine running on a host to a different host over a network. So basically the live migration aspect of it is that the applications and the guest operating system are actually running when that migration happens. Migration is totally useful for load balancing and managing with the hardware and software maintenance activities. And on the concept side, so as the applications run within the VM, they keep modifying the RAM, the physical memory, and they mark the RAM pages as dirty. So in order to make it continue operation on the destination host, we need to actually transfer those dirty pages until a threshold is reached. So it continues on the source host. Then we eventually stop the guest, transfer remaining pages onto the destination, and then resume operation or the execution on destination. So the problem that I mentioned a little earlier with SRIOV VF pass-through is that you need a vendor-specific driver. So here we are showing 2 different NICs on the source and destination hosts. So the source has got a vendor 1 NIC, so you need a vendor 1 driver for it. And on the destination, there is a other vendor NIC that is there. So when we attempt this migration, we need to stop the VM. We migrate this virtual machine to the destination, and then when we resume operation, it doesn't work. The reason is simple, that you need to load vendor 2 driver within the guest in order for it to allow data path. And that's the problem that we see with live migration of VMs using SRIOV VF pass-through. So before I dive deep into vDPA, a little introduction on virtio. So virtio is a specification that defines virtual devices, virtual drivers, and how they interact. The specification also defines how the data plane and control plane is created between the guest and the host. So data plane is nothing but the bulk data transfer that happens between the guest and host and the outside world. And in order to establish this data plane, we need control plane. And control plane basically defines a few concepts like feature negotiation, configuration of the vrings, etc. To make it easy to understand, we have described the vring as just a circular ring of buffers, but if you see the data structures, there are a lot more fields to it. So this is just a very simple representation of that. Virtio data path acceleration, more commonly known as vDPA. So how does it help, right? So data path is actually going between the guest and the device as was in the case of SRIOV VF pass-through. So it bypasses the host kernel and the performance that we require is achieved. However, we have a generic virtio driver. So for other devices like block, this could be a virtio block driver. Here we are showcasing a virtio-net driver. So the control path is actually intercepted by the vDPA kernel framework along with the vendor specific driver. So the vendor specific driver that was earlier within the guest is now actually moving to the hypervisor and on the host machine. So how this helps is that you have a direct data path, but the vendors can easily implement their own control path. Let's talk a little more about the data plane and control plane. So the red line again shows the pass-through data path from the VM to the device. Here I'll take an example to show how this translation of the virtio specific commands happen to the device specific commands. So here you can see there are some vrings shown here. So typically in a virtio-net device, there are pairs of virtqueues for data path. There could be up to n depending on the hardware. And then there is a single control virtqueue for passing on the control information or configuration information like MAC address, VLAN ID, the number of queue pairs that you want to configure. So this is an example where we are passing a command, virtio-net control MAC address set command, corresponding to a command run within the VM. For example, if config ith hardware ether and then the MAC address to configure the MAC address. So virtio-net supports this command. It will be intercepted by the vendor specific vDPA driver, and then it will be translated to the hardware specific command which needs to be which is required to configure the MAC address. For a Xilinx SN1000 device, this is called MC command set MAC. Now we see how actually this vDPA comes into play and how it resolves the problem that we earlier noticed with SRIOV. So again, we have a generic virtio-net driver, and I think this was the cause of concern when we tried live migration with SRIOV. So here we have a virtio-net driver. We have a vendor one NIC on the source host, vendor 2 NIC on the destination host. We have their corresponding drivers in the hypervisor, not the virtual machines. So when we migrate, we have to actually again stop the virtual machine at the source host. We transfer it to the destination. And then when we resume operation, this vendor 2 vDPA driver allows us to easily communicate with the virtio-net driver, and hence the issues with SRIOV VF pass-through are not seen. So everything works well as expected. So we will be going to demonstrate this cross-vendor live migration. So this is the setup that we want to just talk about a bit. So we have 2 physical NICs on the source host. Both the machines are the same Dell 750 machines. The source is labeled as 28, the destination is labeled as 23. We have the Xilinx NIC on the source host, so we produce a vDPA device out of it, the VF, and the SFC vDPA driver allows communication with the virtio-net driver. And next, on the destination, we have a Mellanox NIC, so we transfer the VM and see it will actually maintain data path connection during migration and after migration. So the other NIC on this source host is actually a secondary NIC just to establish data path. So this could be any NIC. So what we are trying to do, we are trying to run iperf from the virtual machine, and then it goes via this Xilinx NIC to the switch, and it enters the data enters into this secondary NIC. When the VM migrates on the destination, the data path would remain the same. virtio-net driver would send packets through the Mellanox NICs to the switch and then to the secondary NIC. So this is how this demo is to be established. In order to allow data path across all 3 NIC ports, we maintain the same VLAN ID on the switch ports, and we are using the AMD Xilinx SN1000 card on the source and Mellanox Connect X6 card on the destination. So over to Eugenio for the demonstration.
Running the, yep. Okay, so here we have 4 panes. The top left one is the source of the migration, and the bottoms one are also in the source of the migration. We can see in the source that we have as a vDPA device in the port v3 that corresponds to the silence virtual function. And then in the destination, we have another vDPA dev in the port 17 that corresponds to a Mellanox virtual function. We will run from the host to the destination. Here, I will send the migration command to the source QEMU, and here we have the iperf server. So I start the source. You can see it's a pretty long command line for QEMU, but it is needed to set the minimum common set of features between the source and the device. You can see that even more parameters like VQ size is set at the minimum between the two, that is 256. And these kind of things happens like transparently. You also need to do this like for all emulated devices. So now the virtual machine starts, it's a Fedora. And now I start the destination QEMU. The command line is exactly the same except for the incoming parameter here that tells QEMU not to start the virtual machine, but wait for another QEMU instance to send it the virtual machine. So I perf start. And you can see that we got a traffic of 45 gigabits per second. This is not really optimized. This is only to show that the live migration is possible and it works, okay? It doesn't have anything like CPU pinning or anything like that. And it's even using an, let's say, or not totally efficient virtue format that is called the split virtue. After that, we send the migration command here, and the device is suspended, and we switch to a mode that allows us to track the memory that the device is writing into. So the source QEMU knows that it needs to send those pages, those memory again to the destination because they are updated, and the destination guest should see a coherent view. After a while, the virtual machine is migrated, and we have all the performance again. So, okay. So we are going to do a little bit deep dive on how all of this work. As Gautam said before, the control virtue is bypassing QEMU. It reaches directly to the host kernel space. This is a problem because we need to migrate the device state that is composed by, as Gautam said, the MAC address, virtues, VLAN configuration, etc. And QEMU needs to track this device in order to be sent. So this is a problem. For example, if the guest tries to change the MAC address, the guest is updated, the device is updated, but QEMU is not aware of this change. So it will send a bad configuration to the destination, and the guest will see this change in the configuration suddenly. So the solution, as many other problems, is to add a new layer of indirection. From now on, the guest will talk with QEMU instead of the device, and QEMU will be able to track all of that. This is only for the control virtue, not the data path. The data path gets all the performance, everything. The data path is passed through. But for the control virtue, QEMU will be able to inspect these kind of changes. So if we do again a MAC change address, it's propagated to QEMU, and then the device reads the QEMU vring. This is the actual Shadow Virtqueue, okay, not the guest one. When the device says it's okay, we can change the MAC address, everything is correctly updated. So good, so far so good. Next step is to actually transfer this state. There is no code change needed for this because emulated devices already needs to transfer all of these states. So all of that is totally reused. So the source have a few state noted, and then it sends to the device. Now, how to set all of this state to the destination device? Well, the destination device already knows how to handle all of these control virtue commands. So the trick is easy. We just enable the control virtue. We don't enable the data path, so the device will not try to write, for example, in invalid queues, or it will filter out valid packets. So after that, only the control virtue commands are sent. Again, the device and the driver already needs to know how to handle these commands. There is no change, totally transparent for the device, totally transparent for the guest. After all configuration is updated, we can enable the data virtue, and the guest can continue happily after that. There is still one problem left, and this how to track this device memory modification. Since it's pass-through, we have no way to tell QEMU that it needs to resend that piece of memory. Well, the solution is actually, again, to reuse the Shadow Virtqueue here. So to track, the Shadow Virtqueue already reuse all the emulated device code. So the track multi-memory is already in it. It was already there before implementing Shadow Virtqueue, so it's for free in terms of code. And every optimization that we do, either way, will benefit both. So how does it work? We need to actually stop the device and tell the device to start reading in this new Shadow Virtqueue, not to break the pass-through. But we need to do it in a way transparent for the guest, because if not, it will not be total live migration. So how is it done? We first allocate this Shadow Virtqueue vring. After that, we suspend the device and we fetch the Virtqueue state, for example, the indices, etc. So we know how to present the Shadow Virtqueue to the guest. Okay. After that, we totally reset the device and we configure these new vring addresses in this memory. The guest doesn't have any kind of access to these new vrings. After that, the device continues as usual. The device, again, this is transparent for the device. The device doesn't know if it's writing to the Shadow vring, to the guest vring. There is no change needed in the device. So for example, when the device writes a packet, it will write to the Shadow vring. When the device is writing to the Shadow vring, QEMU is the one that will forward the descriptor. It doesn't copy the buffer, okay? The buffer is copied directly to the guest, only the descriptor, so it's kind of zero copy in that regard. When QEMU updates the descriptor, it is able to track the memory in the structure it uses regularly, that is the dirty bitmap. So a little bit of recap. I would like to do this. There is no change required for the device in order to track neither the device state, the dirty memory, or to restore the device state in the destination. In the future, it might be possible to opt in or opt out into any of these three items. Okay, so for example, if a device implements its own way to report the dirty memory to QEMU, we can use that. That it could be more performance, but still reusing the other two. Okay, so this is very flexible for vendors. And the changes to the QEMU code is actually really low. The only thing that it's not already there for each feature, for each new virtio feature, is to send the command through QEMU, through control virtue actually. All of them should be roughly the same. So here you can see a few vendors that already supports vDPA. Futures video demo could include like a bigger setup, but we didn't have such big setup with all of these vendors connected between them. But yeah, for future demos, it could be like really great to have all of these and start setting on and off different features, things like that. So after that, Batan will explain more about the Xilinx device.
So these are some details of the Xilinx SN1000 card that we used in the demo. So this is the same card that we developed our virtio or vDPA solutions on. So we have a full-featured virtio and vDPA-net drivers working on this. We also did a vDPA block proof of concept. We do not have that driver in a state where it can be upstreamed. So it's basically one of the industry's first, or maybe the industry's first smartening offering, which actually allows software-defined hardware acceleration in a wide range of areas, for example, networking, security, and storage. So typical applications in these areas include Open vSwitch, In security, you can have IPsec, KTLS, or in the storage as virtio block, as I mentioned. So the major advantage or the highlight of this product is that it includes this FPGA device where the end customers can deploy their own application logic and use that using this P4 programming language so that they can actually tweak the existing custom offloads, or they can add their own new offloads. So in essence, you do not need to change the hardware. It is really flexible. You can add more features just by programming using P4. So this slide captures some of the blogs that are available on the Red Hat website in no particular order, but yes, one can easily go through them to understand more about vDPA. And I think these have been developed over the last couple of years, so very good information over there. And that's all. Thanks everyone for attending this, and time for questions.
Hi. So if we are thinking about safety IO, then I'm guessing Shadow Virtqueue kind of has no chance to work, right? Because the device here thinks that it's accessing guest memory, it's gonna encrypt everything, and then the host cannot understand what's going on, right?
You mean like the encrypted memory, like the confidential computing?
Yeah, that there's extensions where you bring the device into the trusted
Environment. So I'm
trusted
not
everything.
sure if about that. To me, you are exposing like this memory to the device through the IMMU. So I'm not sure if you can like configure the IMMU to trust in that area the same way as you will trust in a guest. I don't have that knowledge. Maybe.
Oh, these are the extensions that we had presentation about yesterday.
I will have to look into that and
So
there is another question at the back.
we can do this one. There is one question on the stream, and the question is: does the vendor-specific vDPA driver in the hypervisor using virtqueues as well?
Using what?
Virtqueues.
Yeah, for the data path. Let me go back to this slide.
So actually the virtqueues are implemented within the device. So the device must be capable of virtio data path. So vendor specific vDPA driver typically implements a set of config operations. So you can see them in a header file called vDPA.h. So the driver needs to implement all of them. So for example, it will implement a config operation like set vring address, wherein for a split virtqueue, you are passed 3 different addresses and you need to configure that on the device so that it is able to write into the guest memory directly. So there are no per se virtqueues within the vendor specific driver. I hope that was the question.
Are there devices already that don't need the Shadow Virtqueue and can do live migration on their own? And do you have some kind of performance ideas on how will it look like?
The performance.
compared?
Still not, yeah. Still doesn't have any kind of figures about that because this, as I said before, this is still, there are a lot of optimizations like low-hang fruit that we can get here. And all of that will require the vendor to actually implement a lot more. So this vDPA framework allows them to only implement that part of virtio, the data path. So this is kind of the main target of this. If the vendor is able to implement all of the spec that the virtio requires for migrating, etc. But now it still doesn't have like those numbers.
Specifically for Xilinx, do you plan to implement it in the device?
I think not in the immediate future, but yeah, possibly sometime later. So yeah, I think the whole idea is actually software assisted live migration. There are solutions in hardware, which we did not use for this presentation.
Thanks.
As I told, I mean, we can like opt in or on and opt out to these 3 different areas, and maybe we can divide in more areas. So maybe one of them, it is worth definitely like to track dirty memory. Maybe others are easier for vendors to implement in emulated or in software assisted way. We can work on that.
Okay, if that's it, then thank you.
Okay, thank you.
Thank you very much.